Yet another method to determine the distance of galaxies, in fact, it is used to determine the distances of the most distant galaxies, is based on type 1A supernovae. First of all, they are very bright. I would like to remind you that we can distinguish between type 1A supernovae and other types from the fact that they contain no hydrogen spectral lines. So as I said, they are very bright and could be observed from great distances. But more importantly, their luminosity is always the same. Why? As we've discussed, type 1A supernovae, basically what happens is we have a binary system of a white dwarf and the regular stars, say maybe in the red giant stage, and there is a transfer of mass from the regular star to the white dwarf. And when the mass of the white dwarf reaches the Chandrasekhar limit, right, then we have runaway nuclear reactions. There is tremendous energy released, and the whole system is disrupted in type 1A supernova explosion. Okay, so their luminosity is always the same, right? Because they occur when the mass of a white dwarf in a binary system approaches Chandrasekhar limit of 1.4 solar masses, right? If you will, there is always the same amount of explosive, and therefore the energy output is always going to be the same. So and we can measure the luminosities of nearby type 1A supernovae, for which we can determine the distance using other methods. So once we've calibrated their energy output, then we can use that. So when we see type 1A supernova going off in very distant galaxy, we measure its brightness here. We know its energy output, luminosity, and then we use the usual relation between the brightness, luminosity, and distance. And then using this relation, we can deduce the distance. And using this method, astronomers have found out something totally unexpected about our universe. It was formed, and we'll discuss that in detail later on, in an event called the Big Bang, some 13.7 billion years ago. And ever since, the universe is expanding because the space and time itself are expanding. But using this method, astronomers have actually determined that as of 4.5 to 5 billion years ago, the rate of the expansion is accelerating. So the universe is expanding not at a steady rate, or that the expansion is slowing down as the mass in the universe is trying to halt the expansion with its gravity. No, it was expanding like that, and then something happened 4.5 to 5 billion years ago, so that the rate of the expansion started to increase, or the expansion started to accelerate, as it is often said. And to explain that, astronomers had to invoke the concept of so-called dark energy, different from dark matter that we talked about. And it turns out from observations that most of the stuff in the universe, almost 70%, is dark energy. And we, just like in the case of dark matter, we have no clue what it is. There are some guesses and hints, but in reality, the honest answer is no idea. Okay? So if you want, we understand today only about 5% of the stuff in the universe. the so-called normal or baryonic matter.